Hello everyone, I Dr. Rashmi Agarwal, Associate Professor, Electrical Engineering Department of J.C. Bose University of Science and Technology, YMCA Faridabad, is going to present a presentation of combined cycle power plants for the module of power generation technologies. The content of today's presentation includes the introduction along with the history, then definition along with the components of combined cycle power plant. Then we will discuss the working principle and combined cycles on which the power plant works. After studying the combined cycle, we will move to thermal analysis of combined cycle, advantages, disadvantages and future prospect of combined cycle power plant. So, we are going to start with the introduction. Combined cycle power plants represent an innovative and efficient approach to harnessing energy resources. By combining gas and steam turbines, they maximize energy extraction from a single fuel source, reducing waste and emissions. This integrated design significantly improves energy utilization, making combined cycle power plant more environmentally friendly and cost effective. They adapt to varying energy demands with quick startup times, enhancing grid stability and meeting peak power requirements. So, in an era where sustainable energy management is paramount, these plants exemplify the better utilization of resources, minimizing environmental impact and advancing the reliability and sustainability of our power generation systems. So, the use of combined cycle configuration is not new. The first recognized combined cycle plant was installed by an Austrian utility, Newag, at their Korenberg A plant in Austria in 1961. Today, large combined cycle plants have efficiency of over 60%, which we can compare to a typical large coal fired plant with an efficiency of around 32 to 37% and a large simple cycle natural gas fired combustion turbine with an efficiency of 35 to 40%. So, this high efficiency is why combined cycle plants have become the configuration of choice for new grid connected natural gas fired generating plants. So, then what is combined cycle? Why we are studying combined cycle? So, combined cycle power plant frequently identifies as CCPP shortcut is essentially an electrical power plant in which a gas turbine and a steam turbine are used in combination to achieve greater efficiency than it would have been possible. So, as we all know that gas turbine plants are generally used for supplying peak loads with other type of power plants like steam or hydropower plants, because gas turbine plants has a quick starting and good response characteristics. Secondly, the temperature of gas turbine exhaust lies between 400 to 500 degrees Celsius. It contains 70% of initial quantity of energy carried away by the exhaust gases. Due to large exhaust loss, the gas turbine plant has a low thermal efficiency that can be about 30%. Thirdly, the fuel which we used in gas turbine is very costly. Therefore, the cost of power generated by the gas turbine plant for the utility system is very high. So, to overcome this low cycle efficiency, a gas turbine plant may be used in conjunction with a steam turbine plant in an utility based load station to offer the advantages of gas turbine as quick starting and stopping and permit the flexible operation of combined plants over the wide range of loads. So, the figure shows the energy flow in a combined cycle. We can see from the figure that the waste heat from the gas turbine is routed to the nearby steam turbine which generates the extra power. Now, we can have a look over the schematic diagram of combined cycle power plant. So, the overall purpose of a combined cycle power plant is to provide the electricity for the consumer use. The gas turbine produces the electricity and the hot exhaust. The heat recovery steam generator then transfers the heat from this hot exhaust to water in order to make a superheated steam. Now, this superheated steam produced in the heat recovery steam generator is then supplied to the steam turbine through the steam piping. This steam is then used by the steam turbine to make the electricity, and the exhaust steam is then cooled and condensed back into the water in the condenser. So, this was the whole picture how the combined cycle power plant is working. Now, we will take one by one the all components by which this plant is manufactured. So, we will start with main gas turbine. Now, what is gas turbine? This gas turbine uses the natural gas or any other fuel such as diesel or kerosene and compress the air to produce a force to turn the gas turbine rotor that is connected to the generator. So, the resultant hot exhaust gases from the outlet of the gas turbine are then directed to the heat recovery steam generator in order to recover the heat before it is being exhausted to the atmosphere. So, what is the procedure how this gas turbine is working? Now, we will go for that. First one is compression. So, air from the atmosphere is drawn into the compressor as it is shown in the figure, where it is compressed to a high pressure and temperature. This compressed air is then directed to the combustion chamber. Now, in the combustion chamber, what will happen? Combustion. So, what happens? The fuel is injected and ignited, producing a high temperature and high pressure exhaust gases. Then the combustion process releases a significant amount of thermal energy. So, these hot exhaust gases then will flow through the turbine and will cause it to the spin. Now, this spinning motion drives the gas turbine shaft, which is connected to a generator, and thus converting the thermal energy into the electrical energy. Now, we have got a exhaust gases. So, the force procedure is the exhaust. After passing through the turbine, this exhaust gases exit the gas turbine at a low pressure and temperature, and typically at a velocity high enough to drive the compressor and create a closed loop cycle. So, now we have moved to heat recovery steam generator, which captures the exhaust gases. Now, this HRSG, which is a short form of heat recovery steam generator, it receives the exhaust gases from the gas turbine discharge. The exhaust gases flowing in the counter flow direction with respect to the steam water coil cools down by transferring the heat to the steam or water. The flue gas temperature at the stack is about 110 degrees Celsius. The lower temperature of 90 degrees Celsius can be used if the fuel gas is very clean and sulfur free. So, this HRSG is similar to now heat exchanger, in which a shell side carries the flue gas and tube side carries the steam of water. It also has a characteristics of the boiler because there are steam drums which are generating the steam in a separated from boiling water before this is entering to the superheaters. So, this is properly shown in this schematic diagram of the simple HRSG. Now, this HRSG can be horizontal or vertical according to the direction of the flue gas path. Generally, we use the horizontal HRSG, which are the most common, and the vertical ones are limited, very much limited to the installation where the space is very small or tight. So, this HRSG can have a different level of pressure level. So, generally they can have 1, 2 or 3 pressure levels according to the size of the plant. We can take example that for the plant size of 200 to 400 megawatt, the pressure level used are high pressure, intermediate pressure and low pressure. So, the plants down to 30 to 60 megawatt usually have two pressure levels, that is high pressure and LP, that is low pressure. And if we take a smaller unit, they will just have one pressure level. So, the one pressure level, sometime with the 3 pressure levels, the LP section produce the steam which is needed for deaeration only. So, that was fully about the HRSG. Now, the next component is steam turbine. So, what the steam turbine is doing in a combined cycle? It is extracting the energy from the steam and converting it to work, which rotates the shaft of the turbine. So, the amount of energy that the steam turbine extracts from the steam depends on the enthalpy drop across the machine. So, this enthalpy, that means of the steam, is a function of its temperature and pressure. So, once we know the inlet and outlet temperature and pressure, we can use Mollier diagram to determine the amount of energy which is available at that time. And if we see, then this steam turbine size range from few kilowatts to over 1000 megawatts. Now, this is we were talking about steam turbine and it has been properly shown in the figure. So, now this when the steam turbine is working, there are different operating control modes, and generally this steam turbine operates in the 3 control modes. So, firstly it is fixed pressure mode, in which below 50% load, which corresponds to about 50% of lime steam pressure, the steam turbine will be operated in a fixed pressure mode. In this mode of operation, pressure from the steam generator remains constant and is controlled by the main control. So, in case the steam turbine is not taking all the produced steam, the pressure of the steam turbine is controlled by the bypass valves. The next mode we will talk is sliding pressure mode. So, when the 50% load is reached, the main control valve is fully open. Now, with increasing gas turbine loads, the steam turbine will be operated in a sliding pressure mode, in which the live steam pressures varies proportionally with the steam flow. The third mode is load control, where the generator is synchronized to the grid. So, if it is synchronized to the grid, that means its frequency is governed by the grid. Then the turbine controller of steam maintains the base load by adjusting the steam flow. So, next component we will talk is about condenser of combined cycle power plant. We can also say the balance of the plant is comprised of condenser, condensate and feed system. The purpose of this condenser is to receive steam that has been exhausted from the steam turbine and then condense it back to the water. Now, this is how performed. This is performed by running the cooling water through the tubes in the condenser, which absorbs the heat from the exhausted steam in order to turn it back to the water. This water is then pumped from the condenser to either a deaerator or the low pressure steam drum by the condensate pumps. Then the feed pumps take suction from the deaerator or low pressure steam drum to provide the water for the high pressure and intermediate pressure steam drums. This is properly been depicted in the figure. There are some other accessories also of combined cycle power plant, like we can start with air cooled condenser. It is shown in the figure also that it condenses, as the name tells, it condenses the turbine exhaust steam or the de-superheated steam from the turbine bypass. Then this condensate collected in the steam condensate header streams under the gravity to the condensate tank, from where it is pumped by the condensate extraction pump to the boiler system on the level control. Now, this condensing systems can be of different types, and the selection of a condensing system for a combined cycle power plant varies based on the environmental condition. So, we can have different categories like water cooled surface condensers and wet condensing system, or air cooled condenser or any alternative condensing system. So, next component we can also talk about the air extraction system, because it is also a very important part of combined cycle power plant. Why? Because the non-condensable has to be evacuated from the condenser before steam can be introduced at startup and should be continuously removed during the normal operation. This startup process is called hogging process and this normal operation is called holding process. So, for the hogging process, the requirements are to lower the pressure as quickly as possible from the atmospheric pressure, which is generally 946 mbar to 250 mbar within the 30 minutes. This is process is called hogging process. Then what is the holding process? What happens that once the vacuum is established and during the normal operation, the hogging extraction skid is shut down and one holding vacuum is set continuously to remove the non-condensable. Next part we can also, which is also very important, that is bypass stack and diverter. What happens? In some instances, when electric power generation is a must, it should be possible to run the gas turbine in an open cycle and exhaust the flue gas into the atmosphere instead of sending it to the HRSG regardless of low efficiency. So, this at that time requires a bypass stack and diverter that closes the path to the HRSG and open it to the atmosphere through the bypass stack. Then the diverter is connected to the GT exhaust duct before the diverging cone of the HRGC, and this implies that gas turbine has to meet the plant emission limits as any SCR in the HRSG is also bypassed. So, the most important characteristic of a well designed diverter is its ability to completely switch the flue gas from the bypass stack to HRSG under all operating conditions. This was the whole discussion about the components of combined cycle power plant. Now, that means we know about the principle of combined cycle power plant. So, we should now discuss about the working principle of combined cycle power plants. So, following steps are carried out in combined cycle power plant to produce the electricity and captures the wastage heat from the gas turbine to increase efficiency and electrical output. So, what first procedure? Gas turbine burns the fuel or the gas. Now, the gas turbine compress the air and mix it with the fuel that is heated to a very high temperature. Then the hot air fuel mixture move through the gas turbine plates, make them spin. Then this fast spinning of turbine drives a generator and that converts this spinning energy into electricity. So, in this arrangement, this gas turbine can be decoupled from the operation of steam turbine, allowing for the steam turbine to shut down with continued gas turbine operation. So, it is always desirable that exhaust gas turbine temperature of the gas turbine should be above 570 degrees Celsius, otherwise the steam cycle will be insufficient, resulting in the lower combined cycle efficiency. After components and working principle, now we should concentrate on the increasing the efficiency of the combined cycle power plant. So, several optimization studies and research was carried out and were developed new technologies to eliminate carbon dioxide and improve the thermal efficiency for the same fuel flow rate used in the traditional cycles. So, our purpose is to minimize the emission of polluted gas and increase the gas turbine mass flow rate used in a steam injection system that permitted an increase of gas turbine cycle efficiency of about 0.11% for each 1% of the steam injected. So, there were different designs were designed for increasing the thermal efficiency. Why? Because due to the excessive demand for electricity, new technologies are developed in power plant cycle in a aim to improve its performance. And the different designs and comparison were made in the following slides that to increase our thermal efficiency. So, first one is simple combined cycle with a steam injection. The second one is combined cycle with a steam injection and compressed air cooling. The third one is the combined cycle with a steam injection into the combustion chamber and steam extraction from the steam turbine. The last one we can consider a combination of your second and third cycles. So, first one I was talking about simple combined cycle with a steam injection, and this is a combination between the Brayton cycle with the steam injection system in a combustion chamber and then using natural gas as a combustible at a steam turbine cycle. In this, as shown in the figure, a monopressure HRSG is installed at the gas turbine outlet in order to generate the required steam flow rates for the steam turbine. Now, for the second cycle, that is steam injection combined cycle with the air combustion cooling, the steam injected in the combustion chamber is not produced in the HRSG as for the first installation, but it is generated by the heat recovery system installed between the compressor and the combustion chamber. So, a heat transfer is made between the compressed hot air and water. Now, this compressed air is then cooled and then entered into the combustion chamber. The supplied water is then heated and evaporated in order to be injected into the combustion chamber as it is shown in the figure. This technique permits to increase the air density flowed through the combustion chamber. As the increase of air density, then the air mass flow rate increases and consequently the gas turbine efficiency can be improved. In addition, steam generation is occurred outlet of the HRSG. This can preserve more heat to the steam turbine cycle. So, in the third design, a steam is extracted from the steam turbine at two different pressure level with two open feed water heater. Now, this steam extraction permits to reduce the flow rate through the condenser and consequently minimize its sizes. This can also decrease the investment cost of the installation. So, as we told that fourth one is a combination between the our second and third cycle. So, it is a combined cycle with the steam injection in the combustion chamber, compressed air cooling with two extractions from the steam turbine. So, we have improved the thermal efficiency, but this installation is more complicated and we need more control and regulation. So, after studying the designs, now we come to a very important topic of combined cycles on which this plant operate. So, as we know that in combined cycle power plant, how the electricity is produced? It is produced by two turbines, that is gas turbine and steam turbine. The gas turbine is operated by the combustion products of the fuel which is on the Brayton cycle, while the steam turbine which operates on Rankine cycle and it is operated by the steam generated by the HRSG from the heat content of the exhaust gases leaving the gas turbine. So, that is why the name is provided, because the gas turbine operates according to Brayton cycle and the steam system is operating according to the Rankine cycle. So, we have two cycles which are joined to generate the power combinedly. So, as we all know that gas turbine cycle works in a high temperature range. So, once the work is produced by the Brayton cycle, the exhaust gas is routed to the nearby steam turbine for producing the extra power by the Rankine cycle, which is shown in the figure following figures how Brayton and Rankine cycles are combined together. So, that means first I will talk about Brayton cycle. Here the atmospheric air is continuously drawn into the compressor where it is compressed to a high pressure. Then this air enters into the combustor where it is mixed with the fuel and combustion occurs. Now, the combustion products expand through the turbine and then they are subsequently discharged to the surroundings. So, this has been shown in the properly in the figure. So, as I told you that your steam power plant is working on Rankine cycle. What happened? In the turbine, there is an isentropic expansion of the working fluid through the turbine from the saturated superheated vapor at the state 1 to the condenser pressure. Then in the condenser, there is a isobaric heat rejection. Now, the heat transfer from the working fluid as it flows at a constant pressure through the condenser. Then we come to the pump. Now, this isentropic compression in the pump to the stage 4 in the compressed liquid region occurs. And then we come to the boiler where there is a isobaric heat addition. Now, what happens? The heat transfer to the working fluid, it flows at a, because it is isobaric, so it flows at a constant pressure through the boiler to complete the full cycle. Now, we are going to combine both the cycles. So, as we see that gas turbine plant, it operates from 300 to 1300 Kelvin, but it rejects the heat at a high temperature level of 800 Kelvin. And in the lower figure, we show, it has been shown that the steam turbine plant reach a maximum working temperature of only 800 K, but their waste heat is released at a temperature which is close to the that of the environment. So, combination of these cycles as shown in the figure cover the largest area on the temperature entropy diagram, and this results in a highest Carnot efficiency of 70%, where the best single cycle efficiency just approaches the 56%. So, that means the gas turbine cycle which works in a high temperature region. So, once the work is produced by the Brayton cycle, the exhaust gas or heat is routed to the nearby steam turbine for producing extra power by the Rankine cycle, which is shown in both Brayton and Rankine cycle. Now, after that, the gas and vapor power cycles are combined using an interconnecting heat recovery steam HRSG generator that serve as a boiler for the vapor power cycle. So, this combined cycle has the gas turbine's high average temperature of heat addition and the vapor cycle's low average temperature of heat rejection, and thus the thermal efficiency greater than either cycle would have been individually. So, now if we go for a thermal analysis, we should know what are the thermodynamic principles. They are usually, because we have studied the combined cycle, so we should also do the thermal analysis of combined cycle. Now, which is based on thermodynamic principle, which are used to determine the energy content of a system and to calculate the system efficiency. So, as we all know that energy balance for a system is the process in which there is a difference of input energy and output energy, that is the total energy which is going to the system. So, the overall efficiency now can be derived that the heat received by the gas turbine as Q in and the heat rejected to the atmosphere is Q out. So, the heat out of the gas turbine is denoted by Q1. So, the hot exhaust gases from the gas turbine pass through a heat exchanger where they are used as a heat source for the two-phase Rankine cycle, so that the Q1 is also the heat input to the steam cycle. Therefore, the total efficiency is the ratio of total work upon Q in, that means WB plus WR upon Q in, where the subscript refers to the combined cycle and work done by the Brayton cycle and the Rankine cycle respectively. So, from the first law of thermodynamics, the overall efficiency can be expressed in the term of heat input and the heat rejection of the two cycles as using the quantity Q1 bar that denotes the magnitude of the heat transfer. This has been shown in the formula. So, in this formula, the first square bracket term on the right hand side is the Brayton cycle efficiency and second is the Rankine cycle efficiency. So, we can derive the combined cycle efficiency, which is equal to efficiency of Brayton cycle plus the efficiency of Rankine cycle minus the product of Brayton and Rankine cycle. So, now we will understand the performance of combined cycle power plants. The most important parameter which affect the efficiency and specific output of the simple gas turbine plant are the compressor pressure ratio and the turbine inlet temperatures. So, the optimum pressure ratio with respect to the specific output is not the optimum one for the thermal efficiency. So, the designers choose a pressure ratio which maximize overall economy of the plant. So, firstly we will come for the compression pressure ratio, which is the compressed air cooling process which increase the cycle efficiency of about 1%, while the optimal compression ratio is same compared with the simple combined cycle. Now, the steam extraction technology leads to the increase of the cycle efficiency of about 2% and decrease the optimal compression ratio from 21 to 20. So, combining compressed air cooling with the steam extraction process improves the sensitivity of the skill efficiency, which is about 50% obtained for a compressed ratio of 18. Now, another main one is the influence of the air excess of the turbine injection temperature, that is the influence of air excess on the gas turbine inlet temperature, which is shown in the figure, which decrease significantly with the increase of the air excess. So, now we will move finally to the advantages, which is increase overall power plant efficiency, reduce investment cost, reduce water requirement. We can also install in the phase, and because it is fully automatic, so we need the less staff, and it is having a very lower environmental impact. So, that means we need a lower maintenance and internal installation cost. But there are some disadvantages also, because it is a big plant. So, technologies are complex and expensive, which increase the initial investment. Efficiency of part load demand is poor. So, thirdly, because we are operating at a very high temperature, so we need special metals for the manufacture of combined cycle plant, and there is a limited fuel switching capability. So, these are the some application we can use for the base load and peaking plants. We can use for the single shaft and multi shaft configurations, and thirdly we can use for the cogeneration, because some CCPPs are configured for cogeneration or combined heater power plant application. In this setup, the waste heat from the HRSG is not only used to drive a steam turbine, but it is also used for the industrial purpose or district heating or maximizing the overall energy efficiency. So, for what more advanced we can develop in future, because already ongoing research and development efforts are focused on improving the efficiency and performance. So, we can integrate it with the renewable energy. Once it is integrated, such as solar and wind, then it provide a more reliable and stable electricity supply. And we can also make a hybrid and integrated energy systems. Nowadays, it is generally increasingly being incorporated with hybrid and integrated energy systems. So, because this system aims to enhance grid resilience and optimize energy generation. Thank you. That was all for this presentation.